Maritime cargo flow is defined by massive scale and slow, relentless movement. But beneath this heavy steel exterior, global supply chains behave like fragile physical organisms, highly vulnerable to sudden shifts in pressure. In 2022, the conflict in Ukraine generated a severe demand shock, forcefully redirecting regional maritime traffic south to the port of Constanta in Romania, straining the absolute limits of its physical infrastructure. At one specific bulk cargo pier, the initial traffic increase appeared manageable. Between 2021 and 2023, the number of vessel arrivals climbed by a steady, linear 35%. This chart tracks annual expenses against CO2 emissions. While vessel traffic grew by a third, congestion-related carbon emissions exploded by 820%. Following the blue bars, the financial damage tracks perfectly, as total operational expenses surged from 2.21 million to 10.66 million euros. The cause of this financial spike was a severe operational bottleneck. Average vessel wait times at the anchorage zone escalated from a baseline of 87 hours to a staggering 788 hours. The pier mathematically possessed the capacity to process every arriving ship, yet even with theoretical space on the schedule, the entire system suffered an absolute operational and environmental collapse. To diagnose the failure, we evaluate the pier's system utilization, represented by the Greek letter rho. This is the standard operational metric defining how intensely a port's infrastructure is used, calculated by dividing the arrival rate by the service rate. In 2021, the Constanta pier operated at a comfortable utilization rate of 0.524. By 2023, the influx of diverted traffic drove that rate up to 0.900, bringing the pier to a state of near saturation. A common logistical assumption dictates that as long as utilization remains strictly below 1.0, the system retains stability. In theory, the queue is mathematically guaranteed to clear. This graph plots the reality against the theory. The green utilization line rises, but remains safely below the 100% threshold. Yet, right at the 0.900 mark, the red line, representing average wait times, diverges completely, curving exponentially upward. We can isolate the cause by examining the nearby port of Varna. Governed by similar EU regulations and utilizing comparable infrastructure, Varna serves as a structural control case because it did not absorb the redirected geopolitical traffic. Under normal conditions, Varna operates with a utilization rate below 0.65, keeping wait times under 200 hours. The Constanta pier operated under the exact same structural rules, but completely broke down under demand. Static infrastructure capacity provides an illusion of safety. Pushing a queuing system anywhere near its theoretical limit destroys its resilience, exposing it to rapid failure from even minor demand shocks. We map this failure using the MG1 queuing model. This describes a single-server pier receiving vessels at randomized Poisson intervals and servicing them at variable speeds. To find the average queue length of idling ships, we examine the equation's defining denominator, 1 minus rho. As utilization moves incrementally from 0.85 to 0.90, that denominator, 1 minus rho, shrinks toward 0. Dividing the numerator by an increasingly smaller fraction forces the resulting queue length to scale exponentially. As utilization slides closer to 1.0, the output shoots toward a vertical asymptote. In the physical world, this mathematical asymptote translated directly to ships waiting up to 33 calendar days just to secure berth access. Furthermore, the cargo mix shifted heavily toward massive Panamax vessels. Their extended unloading times artificially lowered the overall service rate, driving the utilization metric even higher and tightening the trap. The collapse at Constanta was not a failure of port engineering or structural design. It was a strict, inevitable adherence to the nonlinear mathematics of queuing theory. A mathematical delay has physical consequences. A ship waiting 788 hours at anchor cannot simply turn off. It continuously burns fuel to power auxiliary engines. The standard fuel profile for these vessels relies on marine gas oil. Burning this fuel at anchor generates a rigid emissions baseline, 3.206 tons of carbon dioxide for every single ton of fuel consumed. Historically, this was absorbed as a localized cost of doing business. Today, the EU emissions trading system and Fuel EU maritime regulations assign a hard, inescapable financial penalty to these emissions. European carbon allowances averaged roughly €87 per ton of CO2 throughout 2023, attaching a direct tax to every hour a ship spends idling. Applying that rate to the delays at this single pier, the 2023 congestion generated an estimated €2.38 million in pure carbon penalty liabilities. These new regulatory frameworks have turned port congestion from a logistical friction into an explicit multi-million euro environmental liability. The MG1 model accurately diagnoses the delay, but it relies on deterministic inputs. It assumes perfect, fixed intervals for vessel maneuvering and safety checks. Reality is entirely stochastic. Heavy weather, pilot scheduling conflicts, and tugboat shortages inject microscopic, unpredictable disruptions into the timeline. To measure the true fragility of the system, we execute a 1,000-run Monte Carlo simulation, introducing randomized variations to the maneuvering parameters and safety intervals. This histogram maps simulated wait times. The vast majority of scenarios cluster on the far left, representing manageable delays. But the simulation exposes a severe tail risk. In rare outlier scenarios, compounding delays push wait times beyond 100,000 hours, spiking carbon emissions to 350,000 tons. This scatterplot maps those extreme outcomes directly against system utilization. Notice how the green data points remain flat until they hit the 0.9 mark, at which point the stability of the system violently snaps, shooting straight upward. These six-figure wait times are not realistic forecasts for a single ship. They are mathematical sirens, warning that the system has entirely lost its capacity to recover from a delay. At near saturation, microscopic scheduling delays do not simply add up, they multiply, transforming minor stochastic friction into a cascading operational collapse. If high utilization guarantees failure under stochastic conditions, port authorities must deploy structural resilience against both the carbon penalties and the nonlinear math. The primary physical countermeasure is cold ironing, or shore power. This allows vessels to completely shut down their auxiliary engines and plug directly into the local electrical grid during the longest phase of their port stay, cargo operations. Comparing the marine gas oil baseline to a fully electrified shore power model yields a 37% net reduction in total pier-level carbon emissions. Bypassing that 37% directly translates into millions of euros saved, shielding shipowners from heavy EU ETS carbon liabilities. To attack the physical queue itself, ports deploy operational countermeasures like just-in-time arrivals, designed to prevent vessel density from compounding at anchor. By holding vessels far outside the regulatory boundary until exact berth availability is verified, just-in-time protocols actively manipulate the arrival rate, preventing the queue length from escalating toward the breaking point. Cold ironing neutralizes the financial penalty of the wait, while just-in-time arrivals prevent the system from reaching the point where the queuing mathematics become unrecoverable. The MG1 framework perfectly maps the breakdown of a single, isolated pier, but global supply chains operate across vast, interconnected networks. Scaling this analysis requires the MGK queuing network model, designed to simulate complex, multi-berth environments that share critical resources like tugboats and harbor pilots. Integrating live AIS tracking data into these advanced models transforms them. They stop analyzing past failures and begin generating real-time, dynamic queue predictions. This forces a necessary evolution in maritime logistics, abandoning static infrastructure planning in favor of dynamic digital twin management systems. In an era defined by unpredictable geopolitical shocks and aggressive carbon pricing, physical port capacity is meaningless without the digital intelligence to master stochastic queue dynamics.